This next lecture has to do with set theory. So chapter 2, we turn the corner from basic problem solving to the very specific world of mathematics known as set theory. And this is things we're familiar with. We learn it fairly early on in the mathematical life of a student, 5th grade, 4th, 5th, 6th grade. And sets of items, usually this is a roster set of items where you have the set A, noted with a capital letter, is equal to, and then we have the squiggly line, and then A, B, C, D, E, closed squiggly line. This is a set of items, the set of letters, small case A, B, C, D, and E. And that's A, set A. Set B has elements C, D, E, and F. Set C has elements E, F, and G. And U, the capital letter U, which is usually identified as the universal set. In other words, that all of these items are part of this universal set of letters A through I, small case letters A through I. Not every item in the universal set is in each or even all three, any of the three of these. And so from this we can draw some conclusions, and I just want to draw conclusions from this, and then we'll talk about some of the more specific problems with that. But from this we draw the conclusion, for instance, that the letter A and the letter B occur only in set A. You'll see that in B, that the letter C and D and E, all three of those have common with set A, and the letter F is also, E and F are also in common with set C. You find in C that E is common to all three sets. Now there's ways of describing this with set notation, and the way equations are written as sentences. The same way set theory can be written as English sentences, but symbolically written as a sentence. We in English will say compound subjects or compound objects. We have compound subjects and objects in set theory as well, and so the symbolic sentences translate into English sentences. And so, as an example, if we say the elements that are both in both A and B. This is the symbolic way of saying and. A and B. The other term that's used for this is intersect. Where do they intersect? Where do they cross? Where do we find elements in A that intersect with elements in B? And the answer to that, again, squiggly line for set notation, is we find the elements that are in both A and B. A is not in B, so that one doesn't work. B is not in B. C is. There's one. There's one that's in both A and B. Both A and B. D is in both A and B. And E is in both A and B. So that's the word and this is the intersection. This is where these two ideas cross or intersect. The other symbol is the symbol for or. This is sometimes called union. A or B. And here we use the conjunction or. We use the conjunction or. We say, is A, the letter A, in either A or B? Yes, it is, so it's included in our element. How about the letter B? Yes, it's there. C, D, and E. And then we find they're also in here. That's cool. We don't run them twice. The set consists of these individual elements. And then we also have one other element that's in B, but not in A. That's the letter F. And so the word or means it's in A, in set A, or it's in set B. A, B, C, D, E, and F. And this is called union, or the unification of the two sets, A and B. Unified them into a new set. This new set, A union B. And we use the word or. They're either in A or they're in B. So we write them all down. Now, there's a few other symbols here that are important. We can, in English sentences, we can say something, we can negate something with the word no or not. So, the way we do this in set theory is we put a little prime mark, a little mark up above the A, and equals, and then we can write this, the set, roster set symbol to then list all the elements that are in the universal set that are not in A. As you'll notice, A is A, B, C, D, and E. So A, B, C, D, and E, that's in the universal set, but F, G, H, I are not in A. So this is F, G, H, and I. This is the set of items in the universal set that are not in set A. So F, G, H, and I. Now, these things can get layered even deeper than this, though. You could have A prime intersected with C. So there we have not in A and in C. Now, not in A is this set here that we just wrote, F, G, H, and I. And which of these elements, F, G, H, and I, are in C? Because this is the word and. It has to be in both, that and that. So if we look in C, and we say, which of F, G, H, and I occurs in C? The answer is F and G. And so there we have the answer to A prime intersect C. A prime intersect C is F and G. Now that tells you the elements that are in a particular set. There's also a symbol for counting how many elements are in a set. And the way this is written is with the little letter small case n, and then open paren like that with whatever set. So let's take this set A prime. Now here's the thing. That asks how many elements, what are the number of elements that exist in A prime? How many elements are in A prime? So we go over to A prime and we say 1, 2, 3, 4. There's 4 of them. F, G, H, and I. There's 4 of them. Now, do not, when you're being asked a number, do not put the squiggly line. Because that means that's a roster of elements. And if you put the squiggly line and the number 4, the person reading that will assume that you've given them an element of the number 4 in the set, but that's not what we're doing. We're asked the question of a number. At the end, you should just get a number. It's the number of items in there. Not a set of numbers, but a number, the number 4. See that? So like for instance, if I ask you what is the number of items in A prime intersect C, this one here, how many elements are in there? We find there's 2 of them. See that? F and G, there's 2 elements in there. And so the number of items in A prime intersect C is, there's 2 of them. All right, so this is some of the basic things. We can compound these even more. And I'm going to come back to this set for the next lecture, but we can even ask things like A intersect B intersect C. That says in A and in B and in C. So what items are in A, B, and C? And the answer is the letter E. E is the only letter that occurs in all of them. And if we say, well, that's that one. If I ask you, what's the number of items in A intersect B intersect C? The answer would be, there's 1 item. Now these can get even more complicated though. We could ask, what is the intersection of A and B union of A and C? So now we have a compound sentence. So what we want to do is find this set and that set, and then ask the union question, the OR question. So A intersect B, we did that earlier. A intersect B is C, D, and E. Union with A intersect C. A intersects C is the letter E. And the union of all of these items this is OR. So C, D, E, or E. So that OR means either it's in this one or that one. So our final set will look something like C, D, and E. All of the elements of that one, all of the elements of this one included because of the OR that's either in that one or that one, but only listed once, even if they occur in both sets. You only list it one time. And so this is how this rather compound sentence right here would be done. It would be solved like that. Now, there's a few other things within set theory that are helpful to know. Sometimes you can have an empty set. You have an empty set. You have a set with nothing in it. Let's suppose we had a set D. And set D was made up of the letter G. And that's all, just that one element G. And we asked what is the intersection of A and D? The answer is there's nothing in there, and it would be written like this. Or it could be written like this. Okay? A 0 with a slash through it. So that's an empty set. This is just the empty set. And if you ask what's the number of items in A intersect D, the answer is that's the number 0. There's none in there. There's 0 elements in there. And so we have that. We also have this symbol. There's a symbol that says this. This is a subset. And so in this case, we have A is a subset of the universal set. Every element that's in A is in the universal set. It is not true, though, that every element in the universal set is in C. So A is a subset of U, but U is not a subset of A. So it doesn't go the other direction. Okay? And so this symbol was subset. In fact, that's proper subset. That means they can't be equal to each other. If they were equal to each other, or they could be equal to each other, it's written this way. A is a subset, could be the same set as U, but it's at least all the elements of U are in A. It is possible, still even written like this, that some elements in U are not in A. So this is a subset, this is a proper subset. We won't use that very much because we're primarily going to focus on moving towards solutions with these Venn diagrams, which is what the next lecture will be about. But I just want to introduce you to the nomenclature here. There are some other items that are also included in the book. The one other thing I want to mention to you is the number of sets that you can make out of a set. Another subset you can make out of a set. For instance, D, we can make the set D itself, G, and we can also have an empty set. So 2, we have 2 items. In this one here, you see C, we can make subsets. We can make the subset, we could have the empty set. We could have the set E. We could have the set F. We could have the set G. In addition to that, we could have the set EF. We could have the set EG. And we could have the set F and G. And then we have one more set. We could have the set E, F, and G. So we see there's in this subsets of E, 1, 2, 3, 4, 5, 6, 7, 8. 8 of them. 3 elements, we get 8 subsets. Now, the reason this is important is there's one other principle here you need to know, and that is that based on the number of elements in a set, 2 to the n is the number of subsets that can be made out of that set. 2 to the n. So if you have 5 elements, it's 2 to the 5th power is the number of subsets you can make. If you have 1 element, it's 2 to the 1st power. You make 2 subsets, as we saw with D, the empty set, and G. That's the only 2 subsets we can make. So that's an important principle, and will come up later on. All right, we'll see you guys next lecture.